Hello everyone, my name is Kainat Yasmeen, PhD scholar of Indraprastha Institute of Information Technology, Delhi. This work is done in collaboration with Dr. Mishra, Dr. Subramanyam, and Dr. Shobha Sundar. The title of my presentation is Generative Design Optimization of Circularly Polarized Fabry-Perot Cavity Antenna. A Fabry-Perot cavity antenna consists of a dielectric cavity enclosed by a metal ground plane and a partial reflecting on either side. Multiple reflection from a single field excitation within cavity enhance the antenna gain. In this work, we demonstrate that spectral distribution of peripheral roughness feature in the unit cell in the partial reflecting surface serves as an important design parameter for the optimization of antenna characteristics. However, the evaluation of each candidate design using a full wave solver is computationally expensive. Instead, we use a generative adversarial network as a surrogate model. The dual network architecture of GAN is preferred over a single neural framework since the latter requires a large volume for training generated over many hours using by measurement or by simulation. The surrogate model facilitates a rapid evaluation of a large volume of candidate design, enabling us to realize that one results in high gain, wide bandwidth, and very low axial ratio. Now, the motivation behind this work is that the antenna often involves optimization of several complicated and irregular geometry parameters in order to meet multiple objectives such as resonant frequency, gain, polarization, bandwidth, and size constant. The procedure involves two time-consuming steps before optimal design is realized. The first step is the synthesis of multiple candidate design for evaluation. Traditionally, antenna parameter were optimized through trial and error. As we can later evolutionary algorithms such as genetic algorithm, particle zone algorithm were explored. In the second step, the antenna characteristics for design were simulated using computationally expensive full-wave EM solver involving FDTD method, FEM method, or method of movements. Several works have also been explored for computationally simpler, simplifying the computation, like machine learning algorithm, ANN, support vector machine, to map non-linear relationship between the geometry parameter and antenna characteristics using training input-output pair generated from EM solver. Once trained, the design process is significantly accelerated with the surrogate model, replacing the EM solver for rapidly generating the antenna behavior for a given set of geometry parameters. Now, in this work, we considered a FPC structure as shown in figure 1. Here, the primary radiator is a patch antenna with a single field mounted on a substrate layer. The patch is designed to resonate at 2.4 gigahertz. The other side of the substrate is partially ground metal plane of copper. The other side of the cavity is enclosed by a superstrate layer, and the inner side of the superstrate is printed with metallic periodic array of 4x4 unit cell in copper to form a partial reflecting surface. Each unit cell of the partial reflecting surface is a rectangular loop with diagonal. The dimension of this basic antenna structure are fixed across all the designs. The design of the unit cell is this design of results in reduced axial ratio to some extent. Now, then peripheral roughness is introduced to the metallic edges along each dimension of the unit cell. Now, the position of metal brick along the periphery of the rectangular loop becomes the degree of freedom of the, for further reducing the axial ratio and while enhancing the gain or bandwidth of the antenna structure. Now, the antenna system with each unique design is then simulated using CST Microwave Studio. Now, since this is a three-dimensional antenna structure, there are approximately 6.4 million cells for each design. So the duration of each design is approximately 75 minutes. Due to the time-consuming nature of EM solver, we explore the GAN architecture to train neural network to serve as a surrogate model. We considered here 300 unit cells design consisting of unit distribution of metallic brick and their corresponding antenna characteristics obtained from EM solver. Now, GAN architecture we have taken here, and during the training phase, the two-dimensional brick position coordinate is concatenated with latent noise and provided it as an input to the generator. And the output of the generator are antenna characteristic, axial ratio, return loss, and gain as a function of frequency. Now, to further improve the axial ratio, we introduced roughness along the peripheries of the rectangular loop. This is the degree of freedom in the choice of distribution of metal brick, where small change can lead to significant variation in the electrical characteristics. Further from the trained model, we generated 500 candidate design for the unit cell by random placement of the brick position, and we fed this brick position as input to the generator, from which we obtained the corresponding antenna characteristics within 20 seconds. Further, on the contrary, if we generate similar characteristic from CST microwave studio, it would have taken 600 hours. So each of these design give rise to variation in antenna characteristics. We show these variation through histogram in figure 4. For conducting measurement, we opt for the design that has high bandwidth, low axial ratio, and high gain. The fabrication is shown in figure 6. Simultaneously, we also generated its characteristic using the EM solver. Then we compare the antenna characteristics generated from GAN, the simulated antenna characteristics obtained from EM solver, and the measured pattern as shown in figure 7. Now the figure shows here the results shows very good agreement between the three sets of characteristics for gain, axial ratio, and bandwidth. Further, we also compare the performance of GAN with two single neural network architecture, fully connected neural network, ANN, and a convolution neural network, trained with the same data as we trained the GAN, as shown in table 2. So the results validate our hypothesis that the GAN with a dual computing network results in lower error than the corresponding single network. As we can see in table 2, the GAN has the lower NMSC. Now, here I conclude that, however, the evaluation of candidate antenna pattern for each such distribution requires approximately several hours with full wave EM solver, since the antenna is a three-dimensional structure. Instead, we train a GAN to serve as a surrogate model using input-output pair of antenna design and their corresponding pattern from the EM solver. So here, finally, we chose the best design out of 500 candidate design, having axial ratio of 0.4 dB and a gain of 7.5 dBi and bandwidth of 269 megahertz in this case. So thank you.